Differentiating is a process really guaranteed to work. Right? If somebody writes down a function and asks you to differentiate it, you can. It might be painful, right? It might involve a lot of steps, but it's just a matter of applying those steps carefully. In contrast, anti-differentiation might be really hard. Let's try a really hard example now. For instance, can you find some function, so if I differentiate that function, I get e to the negative x squared, which is just another way of saying I want to anti-differentiate e to the negative x squared, right? What is that? Well, let's make a guess and see if our guess is correct. I mean, maybe an antiderivative of e to the negative x squared is, I don't know, e to the negative x squared over minus 2x plus c, right? I mean, not saying this is correct, but it could be true. If this were the case, I can check it, right? I can differentiate this side and see if I get this. So let's differentiate e to the minus x squared over minus 2x. That's really the same thing as differentiating e to the minus x squared times minus 2x to the negative first power. So that's a derivative of product, which is the sort of thing the product rule is good for, right? So first I'll differentiate e to the minus x squared, and I'll multiply that by the second term, minus 2x to the minus first power, and I'll add to that the first term, e to the minus x squared, times the derivative of the second term, which is minus 2x to the minus first power. All right, what's the derivative of e to the minus x squared? That's e to the minus x squared, because the derivative of e to the is e to the, times the derivative of minus x squared, which is minus 2x, and then it's times negative 2x to the negative first power, right, plus e to the minus x squared times the derivative of minus 2x to the minus first power. Well, I'll just copy that down and we'll deal with it in a second. Because this is pretty exciting right here, right? This term cancels, this term cancels. This is looking pretty good, right? Maybe the antiderivative of e to the minus x squared really is this, because when I differentiate this thing, at least I get an e to the minus x squared. The bad news is that I also get this term, right? This turns out to be e to the minus x squared. Now I got to deal with this. It's again e to the minus x squared, and then times the derivative of this. Well, when I differentiate this, I get a negative sign times this thing to the negative second power, right? And then by the chain rule, the derivative of the inside, which is negative 2. And yeah, I mean, this is bad, right? I mean, I differentiated this thing right here, and I got back something that included an e to the minus x squared, but also includes this non-zero term. So as a result, this is not the case. Well, that didn't work, but it wasn't for lack of trying. In fact, an antiderivative for e to the negative x squared cannot be expressed using elementary functions. What do I mean by elementary functions? I mean things like polynomials, trig functions, e to the x, log, things like that, right? I mean, this is really a surprising result. I mean, there is a function whose derivative is e to the negative x squared, but it's not a function that I can write down using the functions that I already have at hand. Maybe e to the negative x squared is just an isolated, terrible example. I can't antidifferentiate e to the x using elementary functions. I can't antidifferentiate log x using elementary functions. I can't even antidifferentiate this very reasonable looking algebraic function, the square root of 1 plus x to the fourth. I can't find an antiderivative of this just using elementary functions. So what does this mean? Let's try to summarize the situation. It's not just that many functions are hard to antidifferentiate, it's that many functions are impossible to antidifferentiate. Not in the sense that they don't have an antiderivative, but in the sense that we're not going to succeed in writing down that antiderivative using the functions that we have at hand. In light of the difficulties of antidifferentiating, the fact that there's no guaranteed answer, it means that we should be happy that we can ever evaluate an antiderivative problem, right? It also reflects the fact that some real creativity is needed. You know, if an answer is not guaranteed, then potentially we're going to require more creativity to cook up the answers, even when they exist.